All right, so we're going to be taking notes in your interactive notebook today on exponential functions. You should already have a notes sheet, pre-structured note sheet that looks like this with you now. And ultimately, this is going to be what our final product will look like. You will put this on the right-hand side of your notebook with the title at the top and the windows on the left. And then at the end, we'll go ahead and do a quick summary. On the left-hand side of the same notes page, you're going to put the booklet on on exponent rules that we did last week in your interactive notebook. So I'm going to go ahead and pull this off to the side. This is what our final product will look like. To get this set up, you're going to take the note sheet you have and cut across the dotted line on top. This separates, and this will become the title. Go ahead and put that to the side for now. The rest of this, if you'll notice, let me get a little bit closer. The dotted lines only go to a certain point and then they stop and the lines become solid. You are only going to cut up to those dotted lines. And stop. And then once again stop. And that's because when you turn this over, you'll notice that blank white side. That is exactly what we're going to glue down into your notebook when this is done. And this will get folded in half like this. And then those flaps will go in your notebook. Obviously, try to do that a little bit straighter than I did. It's always the fun of a video, right? Okay, so we're going to go ahead and work on this, and we're going to look at exponential functions from table to equation, and then ultimately how to graph it, okay? When we're talking about exponential functions, there are a lot of similarities to linear functions, but there are a couple of crucial differences that will make that will show you the difference between how we get a straight line to a curved line. Ultimately, what you need to remember with an exponential function is it's a relationship where the x values increase by a constant amount. The y values are being multiplied by that constant amount. This should sound a lot like your geometric sequences. We're talking about numbers that increase or decrease significantly faster than a linear equation. It's a rapid change in movement, which is why you'll see such a dramatic shift in your graphs. So I'm going to go ahead and zoom in for each of these individual sections. In a table, the x values are increasing using addition. So if you notice in these tables, the x values are just going up by 1 to 2 to 3 to 4, but the y values are being multiplied by a constant amount. If you recall back to geometric functions, we call that constant amount the constant ratio. Ratio should sound awfully familiar. In order to find the constant amount or what the ratio is in each table, you're going to need to divide or count backwards, and then you're going to find the y-intercept. The y-intercept, just like in linear equations, is the starting point, or it's what y equals when x is equal to 0. So you can see in this table here, they don't give us an x equal to 0, so we're going to need to count backwards. So you're going to look at the difference to get from 6 to 18. 18 to 54, 54 to 62, what did we do? What did we multiply by? The fastest way to do that would, number one, to make sure that it was constant. In all these scenarios, it will be. But you can divide one from the previous. So I could divide 18 by 6 and discover that that's 3. And then if I continued repeating that, 54 divided by 18 would be 3. So the ratio, the way that the b is changing in this scenario, is being multiplied by 3. And then we want to figure out what our starting point was. If we were multiplying by 3 each time to go up, then if we were to divide this number by 3 to go backwards 1, what was y when x was equal to 0? Meaning, if I were to add another component to this table, what would x have been if I had divided and gone backwards 1? 6 divided by 3 would be 2. So when x was equal to 0, y was equal to 2. That would be our starting point on the graph. Let's try that again with the next table. Here they actually give us what y is equal to when x is equal to 3. So I know our starting point, or our a in this circumstance, is 3. Now the question is, what is b? What are we multiplying to get from one step to the next? 3 times what equals 12? 12 times what equals 48? If you've said 4, you are correct. We are multiplying by 4 to get to each term. In this third table here, we once again are given what x is, we're given x equal to 0, so we know that y, or the a, in this equation will be -2. This is our y-intercept, the exact same way we were doing y-intercept in linear equations. Instead of this being our plus b and y equals mx plus b, this is going to be our a. Notice your a can be negative, okay? That's when we're going to be looking at a decreasing function. So what is our b? How did we get from 5 to 2 and from -5 to -2 and from -2 to -0.08? If you were to put that into a calculator, which I would encourage you to do, you are asking yourself, what did we divide by to get here? Because we're going down, I know that there was division involved, and that would be 0.4, or 2/5 is what we were going down by in this circumstance. All right, last table example here, we're once again not given a 0, so we're going to have to figure out what we're doing to get there. These all stay negative, and remember, a negative times a positive is negative, so we are definitely multiplying by a positive number here to keep it all truly negative. To get from 2 to -8, what are we multiplying by? To get from -8 to -32, what are we multiplying by? If you said 4, you're correct. And so we're going to want to reverse that. We're going to want to go backwards, right? Let's look at this. If we're multiplying by 4, then to go back to when x equals 1, then we are going to need to take that -2 and divide by 4, and we're going to get -0.5. But when x is equal to 0, we're going to have to take that -0.5 when it was 1 and divide by 4 again, and we're going to get -0.125. So our a in this circumstance is going to be -0.125. So we've finished the tables on the left there, and we're going to move on over and look at the equations. An equation for an exponential function, is in the form of y. This is the base or the standard function for an exponential equation. That's going to be y is equal to a, or whatever our y-intercept is, our starting point, times our multiplier, or our growth rate, to the x power. And remember, that x term is the value that is being added here. It is going up by 1 in each of these circumstances, and it's being multiplied by the growth factor. So that's what our b was equal to, and a is the starting point. Let's look at what that would look like if we turned each of these equations into each of these tables into an equation. So in this first, all of these are going to be y equals. You can just go ahead and start with that. So what was our a in this first equation? Our a, or our starting point, our y-intercept in this first equation was 2. Our growth factor was 3. And we're going to multiply that to the x power. You're literally just taking whatever information you had from the table and plugging it in. So then y over here is going to be equal to 3 times 4 to the x power, 2 times 0.4 to the x power, and in this case y is equal to -0.125, also times 4 to the x power. I'm going to go ahead and open the Desmos app on my phone to prove to you some of these circumstances in the table. If I were to take my equation, we said that it was 2 times 3, the growth factor 3, to the power of x. So in this case, what if x was 2? I want to prove if I equal 2 for x in this equation that my outcome will be 18. So to the second power. And if you can look right here in that gray region where the solution on Desmos comes up, whoops, there we go. You can see that that does in fact equal 18, okay? So remember, Desmos.com and the Desmos app are free for you to always check your work. And let's go ahead and use the Desmos app to solve these next couple functions. the function f of x is equal to 1500 times the quantity of 0.995 to the x power, where x is the time in years. This models a prairie dog population. How many prairie dogs will there be in 8 years? So we're saying that we are starting with 1,500 prairie dogs. They're growing by almost 0.995 per year. So how many prairie dogs are we going to have in 8 years? So if I were to take f of x, that x is the time in years, and we just said 8 years. So a function of 8 will be equal to 1,500 times that 0.995 to the x power, or to the 8th power. When I enter that into our calculator here, we're going to have 1,500 times that 0.995 to the 8th power. And that looks like 1441 is what we're going to come up with here. Not sure how to zoom in very nicely for you. So if you can see there, I have 1441. So the population is actually decreasing, which makes sense because this number here, our B, or our growth factor, is less than 1. So that does make sense that the total quantity is going down. So after 8 years, we are left with 1,441 prairie dogs. Okay, let's look at the next example here. A ball rolling down a slope travels continuously faster. So if it says faster, that's your key that this number is going to go up. Suppose the function is equal to y is equal to 1.3. That's kind of hard to see, but that is a 0.3 there, times 1.41 to the x power. This describes the speed of a ball in inches per minute. Approximately how fast will the ball be traveling in 15 minutes? So once again, we're going to take that equation. Y is equal to 1.3 times 1.41 to the x power. That 15 is the x we're looking for. We're trying to figure out how far this ball travels in 15 minutes. So that's equal to y is equal to 1.3 times 1.41 to the 15th power. This number is going to be pretty substantial, you guys. We're starting at 1.3 inches there. But when you multiply something 15 times, you're going to expect it to grow pretty quick. So let's look at that on Desmos again. 1.3 times 1.41, close parentheses, to the 15th power. You see that gray number right there? We're talking about 225.02 inches per minute. For these exponential functions, you're going to expect the decimals to go on quite a bit. Just go ahead and round it to the 10th place, that second number. Since that third number is a 4, it will not round up, so we're going to go ahead and leave that at 225.02 inches per minute. Okay, not too bad there, right? I'm going to zoom back out, and we are going to look at how these exponential functions look on a graph. The graph of an exponential function will always be a smooth curve. That is non-negotiable. We are talking about a smooth curve that is either increasing or decreasing, and it's going to be one of those deep curves that we were talking about at the beginning of the year. To graph an exponential function, choose several values of x. You want both positive and negative, and you always want 0, and generate the ordered pairs. So we're looking at this one. We have -5 times 2 to the x power. So I'm just going to keep using my calculator because I'm encouraging you guys to do the same. Don't make this too hard on yourself. We just conceptually want to know how an exponential graph looks. So we're talking about -5 times the growth factor of 2. And that first x value we have is to the power of -1. The result is -2.5. Okay. And then our next one is we're just going to keep filling in the table. -5 times the same growth factor of 2. The only thing we're changing is the x power. We get -5. And that's because 2 to the 0 power is going to remain, anything to the 0 power is 1. So then you get -5 times 1, which keeps your starting point, or your A, true. And if we're talking about A is always the y-intercept when x is equal to 0. If you look at the function here, a was -5, so I 100% would have expected that to be the case. All right, -5 times the growth factor of 2 to the first power, and we get -10, and that's because 2 to the first power is just going to be 2, and -5 times 2 I would expect once again to be equal to -10. And the next one you could really do on your own. 2 squared is 4. 4 times -5. This should be -20. We can verify that with the calculator again. So that's going to be to the second power. Oops. To the second power. And we do get -20. All right, so now that you have all of those values in the table filled out, you're going to go ahead and graph this. I imagine we should be counting by 2's here on the y-axis. So I'm talking 2, 4, 6, 8. -10 will be about here, or will be there, not about. So if I go to -1 on the x-axis and down just past 2 to 2.5, 0, I'm talking -5. +1, we're talking -10, and +2, we're talking -10, 12, 14, 16, 18, 20. So you can see this is taking a downward curve. I'm just kind of going to sketch that clearly. I missed all my points. Let's try that again when this is angled better. All right. So that's the exponential curve we're talking about there. Not pretty, but it makes sense in context, okay? So you have a downward facing exponential curve. All right, let's do this last example and then we'll get ready to wrap these notes up. The function here is y is equal to 3 times 1/2, or 1/2 to the x power. We're once again going to plug those values into our calculator, 3. Make sure you protect that 1/2 in parentheses. And then use this a to the b power function here to put the, whoops, let me go back, sorry. A to the b power, and that's going to be to the power of -1. That comes up with +6. So when x is equal to -1, y is equal to +6. Once again here, if a is the starting point or the y-intercept, when x is equal to 0, without entering anything in our calculator, we should be able to just go ahead and pull a and plug it right into the table. This should be 3. When I plug that into my calculator, I can confirm when x is equal to 0, y is equal to 3. Zoom in for you there. Okay, let's go ahead and run it. The next value in our table is 1, so to the first power, and x is equal to, or sorry, y, when x is equal to 1, y is equal to 1.5. And last one, when x is equal to 2, y is equal to 0.75. 0.75. Okay, we're going to go ahead and graph those. When x is equal to -1, 1, 2, 3, 4, 5, 6, y is equal to 6. When x is equal to 0, the y-intercept is +3. When x is equal to 1, y is equal to 1.5. And when x is equal to 2, y falls just below 1 at 0.75. You guys see the curve that one takes? Once again, if you sketch and connect your dots, you should get a deep exponential curve. This is probably your first introduction here. Notice how I'm curving this line. The curve continues to get infinitely closer to the x-axis, but will never actually touch the x-axis. If we were to put this in a graphing calculator, which I can do right here on Desmos, that gets exponentially or significantly closer to the x-axis, but it never actually hits 0. It approaches 0. That is called an asymptote. That word asymptote is something. Okay, so as we were saying in this last example here, we curved the line and it got infinitely closer to 0, but it never actually touched 0 on the x-axis. We call that an asymptote. Go ahead and pause the video here and catch up on any notes you may have missed. Make sure that all your graphs and your equations and everything are complete. And then we're going to go on to make sure that this is assembled properly in your notebook and that we get a nice summary in there on the right-hand side. Okay, so you're going to take the windows and flaps you created and fold it over to create yourself windows that open to the left. You've got a blank side here that you will glue down flat into your notebooks. And ultimately, you want it to look just like this. Let me see if I can zoom out for you. So in the right-hand side of your notebook, you're going to take the completed windows and glue them down on the left-hand side and glue the title to the top of your notebook. Trim that down a little bit if you need to help it fit. And then I want you to go ahead and summarize the information that we just did. This will help you quite a bit with your work going forward. I'm going to scroll into the summary. The dependent variable gets multiplied by a constant amount, and the graph will always, always, always be curved. That's how you know it's exponential. When you're looking at the base function, this could also be y is equal to a times b to the x. Actually, that's exactly what I would have put here in my summary. So this is the same thing as y is equal to a, or the starting amount, times b, your growth factor, to the x power. Okay? In this circumstance here, y, or in both circumstances, is equal to the dependent variable. This first number is going to be your y-intercept. It's going to be your starting point, and it is going to be the value of y when x is equal to 0. B is your growth factor here. As you can see here, that's why some functions may reference it as a g instead of a b. That is your growth factor. And then x is the independent variable that dictates how many times something is being multiplied. That is your independent variable. Make sure you go ahead and get the summary written into your notes as well. It is very important. I'm going to go ahead and stop the video here. So pause it and get whatever you need down into your notes.